Hello everyone, welcome to DP Tutorials by Donny Jarua. In this teaching module, we will emphasize on one important topic, which is the finding the magnetic field at the center of a circular coil by using Bio-Savart's law. Okay, so we have learned from Bio-Savart's law that the magnetic field due to the current element, is given by this expression, okay, dB. With the magnetic field due to the current element, IDL, is given by dB equal mu naught divided by 4 pi, okay, IDL sin theta divided by r square. This is the expression for mathematical expression for Bio-Savart's law, and it is the inverse. It is also the inverse square law. So, in order for us to reiterate and recall our previous idea about Bio-Savart's law, is that this dB is directly proportional to the current element IDL and is also inversely proportional to the square of the distance between the current element and the observation point. So also we have learned that if I have any wire, and if the current is flowing to this wire, if I consider any point P which is at a certain distance from the wire, that means there will be magnetic field associated with that point. So this magnetic field will be in the form of closed loops or closed spheres. So these are some of the important things that we have learned from Bio-Savart's law. But the important thing about the Bio-Savart's law is that it does not give us the direction of how to find the direction of the magnetic field. But in order to find the direction of the magnetic field, we have to use these rules which have been laid down over here, like the right hand palm rule. Okay, this is the right hand palm rule, or the right hand grip rule. In the right hand grip rule, okay, we will, if we imagine that if I consider this coil, and on this coil, that means if I have if I consider the direction of the flow of current, like for example, if I consider this circular coil having a certain radius r, then if the current enters in this direction, so let that current be I, and it will move along this circular coil, and it will emerge out from what? From the other end of the conductor. Now, using this right hand grip rule, that means if you want to find the strength of the direction of the magnetic field at the center of the coil, if I want to find the direction of the magnetic field at the center of this coil, then we will apply this right hand grip rule. When we apply this right hand grip rule, that means when we curl the fingers, this curling of fingers will be in the direction of what? The curling of the fingers will be in the direction of the movement of current. So from here, current is moving in the anti-clockwise direction. So from here, when you curl this finger, okay, when you curl that finger, so from here, when you curl this finger in the direction of the movement of current, that means over here, this is moving in the anti-clockwise direction, then the thumb, the direction in which the thumb indicates, that will give you the direction of the magnetic field at the center, okay, at the center O of the coil. So if O is the center of the coil, okay, if O is the center of the coil, that means if I make use of this one, of this right hand grip rule, that means the magnetic field at the center of the coil will be pointing vertically upwards, okay, vertically upwards. In this case, if we are viewing on the screen, that means this magnetic field at this center O of the coil, the magnetic field at the center O of the coil will be directed in the perpendicular directions, vertical and upwards, And in this case, again, if we make use of this right hand palm rule, this will be more effective. Okay, making use of the right hand palm rule will be more effective to find the direction of the magnetic field at the center of the coil. Now, we have also learned that if r is the radius of the coil, that means in order to find the circumference of the coil, we know that the circumference of the coil will be equal to twice pi r, which is the bound length of the coil. Okay. Now from here, if I can divide this length of the coil into many elements, that means from here I can through all these elements, through all these small element DLs, that means I can find the net contribution. I can find the net contribution. So from here, if I consider this element, okay, if I consider this element, let that element be of length DL, then when the current, this will be element of length DL, okay, that will be element DL, and if I consider this element of length DL, with that element of length DL, this will be element of length DL, then the since this current is moving in this direction, okay, the current is moving in that direction, then the current element will be on this same direction, that means pointing on this direction, that will be current element IDL. So the radius vector will be from this point to the center O of the coil. That means the radius vector will be governed by that unit vector r cap. Okay? The radius vector will be governed, the direction of unit vector will be governed by this unit vector r cap. So from here, this is the direction of the current element, which in this case I can represent by this blue colored vector, and this blue colored vector will indicate about what? This blue colored vector will indicate direction of our current element vector. That means I will place that current element vector in that direction. Now, when I use this right hand palm rule, okay, when I use that right hand palm rule, it is obvious that when you place this thumb, okay, you place first your thumb in the direction of the movement of current. You place the thumb in the direction of movement of current. So from here, this thumb is being placed in the direction of movement of current. So that will be the direction of our current element IDL. So this is the direction. This is the direction of flow of current, and this is our current element. So this current element is in this direction. You use your right hand, and when you place your right hand, you have to place your right hand in such a way that your right hand, the palm of your right hand, okay, the palm of your right hand in such a way that the palm is on. Right hand, I will write over here in short, palm up. Okay, this is the palm. This is the palm of your hand. Right hand, palm up. So when you place your hand, right hand, palm up, and with this thumb, okay, with that thumb indicating the direction, with this thumb indicating the direction of flow of current, that means this will be the direction of movement of the current element, and all these outstretched fingers, okay, all these outstretched fingers will indicate the direction of the radius vector. So you point all these fingers in the direction of what? You point all your fingers in the direction of your radius vector r. So when you point these fingers in the direction of the radius vector r, that means from here, that means this will be what? This will be the direction of your radius vector r. So which means that in this case, this palm, that means the palm is facing up. Okay, your palm is facing up. So at this particular point, at the center O of the coil, that means your magnetic field will be moving upwards. Okay, it will be moving upwards. So that is why in this case, when the current is moving in the anti-clockwise direction, according to this diagram, that means the magnetic field at the center O of this circular coil will be directed upwards, since your palm is what? Since your palm is directed upwards. Okay. Now again, let me just revise. You place your current vector. This thumb will indicate the direction of what? That thumb will indicate the direction of your IDL vector, okay, which is your current element vector. Okay, current element vector. Place first your thumb in the direction of your current element vector. Number two, this outstretched fingers in the direction of what? In the direction of R. So next, our outstretched fingers, this outstretched fingers in the direction of what? This outstretched fingers in the direction of what? In the direction of what? R bar. Okay, our outstretched fingers in the direction of what? R bar. So the direction in which this outstretched fingers in the direction of R. So this palm, your palm is facing up. So when your palm is facing up, which means that the magnetic field, this palm, okay, this is your palm, okay, this is the palm of your right hand, okay, this is the palm of your right hand. So if your palm is facing this side, this will give you what? This will give you the direction of your B. Okay, that will give you your direction of the palm on when the current is in the anti-clockwise direction. Okay. Next, number 2, we will reverse the direction of current flow. When we reverse the direction of current flow in such a way that the current, the current enters from this point. The current enters from this point. That means in the clockwise direction. The current here will be in the what? In the clockwise direction, and it will move along the circular coil, and then it will come out from this edge. So this will be the direction of flow of current. First case, we consider the case in which the current is in the anti-clockwise direction, and next case we will consider the direction of the flow of current on the coil in the clockwise direction. Similarly, over here also, the radius, the circumference of the coil will be twice pi r. So, in order to find the magnetic field due to all the coil, you have to consider to all the circumference of the coil, which in physics we consider for small elements. If we can find out the magnetic field due to this small element, and if we can find out the magnetic field due to this small element, also if I can find out the magnetic field due to this small element dl, that means if I integrate over all these small elements, that means that will give us the total contribution to all the elements due to all the elements will give us the magnetic field due to this entire circular coil at the center O of this circular coil. So O is the center of the coil and R is our radius vector. R is our radius vector. So from here, see, the current is moving in this direction. You have to be very careful with the direction of current. Like in this case, the direction of current is in this direction. So our current element is in this direction. IDL is in this direction. IDL is in this direction. IDL is in this direction. Even from here, the current is moving in this direction. So the current I is moving on that direction. The current I is moving in that direction. And from here, if I consider a small element dl, if I consider a small element dl, then our IDL vector will be on this direction. This will be the direction of what? This will be the direction of what? IDL vector. So from here, again, if you use your right hand palm rule, I will take this vector, and this blue vector will give us our what? Our direction of our IDL vector. So our IDL vector will point on this direction. He will point on that direction. So from here, using this right hand palm rule, from here you will have to orient your right hand. You have to arrange your right hand in such a way that your right hand faces the palm. Your palm of your right hand in this particular case should face down. When the palm of your right hand is facing down, that means you first orient your hand, align your hand in the direction of what? In the direction of your current element. So from here, the current element is in this direction, so this will be what? The direction of our current element, IDL vector. So from here, this will be our IDL current element, the thumb. Thumb is the direction of the current element. Then your outstretched fingers, these outstretched fingers will give us the direction of what? Of our radius vector. This outstretched finger will give us the direction of what? Of our radius vector. But since the direction of your palm, the right hand of your palm, is directed downwards, your palm is facing downwards, so that is why at the center O of the coil, this palm will be facing down, and the center O of the coil, that means your magnetic field at the center O of the coil will be directed downwards. So if it is directed downwards, we can represent the magnetic field at the center O of the coil by a cross mark. Indicating that the magnetic field, is directed downwards. So from here, we can represent this in this form. At the center O of the coil, the direction of the magnetic field will be directed downwards, indicated by that cross mark, which means at the center O, if the current is clockwise, the direction of the magnetic field will be downwards since the palm is down. And from here, when the direction of the current is in the anti-clockwise direction, the palm will face up. So when the palm is facing up, so the magnetic field at the center O of this coil will be represented by that dot. Okay, so these are some of the important characteristics that we need to know using what? Using the right hand palm rule and the right hand grip rule to find what? To find the direction of B. Okay, to find the direction of B. Since B, magnetic field B is always a vector quantity. So from here onwards, we can just deduce the expression for finding the magnetic field. So from here, let's consider let us consider over here the circular radius of radius r, carrying a current I. And from here, what is the current element? The current element is one, then IDL. This IDL bar is the current element. Sometimes students make mistake by asking a question, why you write IDL and not IDL bar? If you put like this IDL bar, this is totally wrong. Why? Because current is one. Current is a scalar quantity. It is nothing but the movement of charge per unit time. Current is nothing but movement of charge per unit time. So when I say current element, this current element, even if current is a scalar, this itself, the current element is a vector quantity. Okay? Our current element is a vector quantity. So when we represent current element, we write IDL bar. And R bar is one. R bar is our position vector. Okay? Position vector of one. Of the current element IDL. Of the current element IDL with respect to the center O of the coil. Then from here, our R cap is the unit vector. Even from here also, if this is R bar, the direction of R bar is always directed from the current element to the center O of the coil. So that will be the direction of our current element R cap. So from here, using Bio-Savart's law, okay, we can find the the magnetic field. Okay, so we'll apply Bio-Savart's law to find the magnetic field at the center O of the current element due to the current element IDL. So what is this? We can write, that means this current element dB will be equal to 1 mu naught divided by 4 pi, okay, IDL cross R bar. I can write first in this vector form. Okay, IDL cross R. Okay, IDL cross R. IDL bar cross R bar divided by 1, divided by the R cube. So this is our one. This is our Bio-Savart's law. Okay, this is our Bio-Savart's law in vector form. Okay, in vector form. Or in the exams, you can directly start from the scalar form. You can simply write dB equal mu naught, okay, divided by 4 pi, okay, IDL, okay, sine theta divided by 1, divided by R square. This will be Bio-Savart's law in 1. This will be Bio-Savart's law in scalar form. You can directly start from here, but in this case, I will start from the vector form. Then, this R bar, we can convert from the vector form to the scalar form by using some relationship. We know that unit vector R is given by this expression. Okay, is given by this expression, R bar divided by modulus of that vector. Okay, the modulus of that vector. So the modulus of that vector is R bar divided by R. And from here, if I want to find out this R bar, okay, if I want to find out this R bar, that means our R bar in this case, okay, our R bar in this case will be equal to what? Will be equal to R cap, cos multiply this R this side, so you will get like this. Now keep in mind, okay, that this expression dB bar, okay, dB bar mu naught divided by 4 pi, okay, mu naught divided by 4 pi I dl bar. That means if you write like that, that means we can write like this R bar. That means the moment we change into the scalar form, it will be expressed in that form, because this is nothing, this IDL is nothing but the first vector, and that R bar is what? Is the second vector. So we have to use the cross product, okay? Cross product of two vectors, which in the formula, the cross product of two vectors will be A bar cross B bar will be equal to 1. AB, okay, sine of theta, then this will give you 1. This will give you n cap. That n cap is what? R cap vector. So from here, these are nothing but key points that we need to remember. Okay? Key points or key ideas that we need to remember. Okay? So from here, then we will mark this. Let us mark that as equation number 1. Okay. So from here, this equation 1 reduces to, so from here, from this scalar, from this vector form dr bar, now we have to write only in scalar form. So you should not write any dB bar. Then from here you can write mu naught divided by 4 pi. Okay, mu naught divided by 4 pi. Then we have I dl. Then from here we have 1 in place of that r bar. Okay, in place of that r bar, in place of this r bar, we substitute by this expression, which is, okay, r cap divided by r cube. And with what? Since we have removed, okay, since we have removed this cross product, since we have removed that cross product, we have to put sine of theta. Okay, we have to put sine of theta, where theta is the angle between what? Is the angle between IDL and R. Why is what is the angle over here? IDL and R. This is the angle between IDL and R. From here, yeah, this is the angle. Even in this case, this is the angle between IDL and R. In this case, this is the angle between IDL and R. Okay, your IDL is in this direction. Okay, IDL in this case, thumb in this case, and our R. This is the direction of our IDL vector. This is the direction of IDL vector, and this is our R vector. So the angle between I and DL is in this direction. For this case, that means thumb is pointing in this direction. So this will be the direction of what? This will be the direction of IDL, and R is in this direction. So that is our R vector, our radius vector, the first vector, the second vector. Then from here, this is the angle between IDL and R. So that is the most important thing that we need to know. Okay, so from here, this and this can be cancelled. So we got, okay, dB, this dB will be equal to mu naught divided by 1, mu naught divided by 4 pi, okay, IDL. Then over here, this will give you 1 sine theta divided by 1 divided by r square. Why? Since, okay, since this unit vector r cap, the modulus of the unit vector r cap is simply equal to 1. The modulus of it, since this is 1, since it is a unit, okay, it is a unit vector. It is a unit vector. So from here, okay, so from here we can, this is 1. This is the magnetic field. Okay, this is the magnetic field due to that current element. So this is nothing but the magnetic field due to that current element. So this will be, in order to understand, that means this is the magnetic field due to that current element. Due to 1, due to the current element. So that current element, that small current element, IDL. Okay, so this which we have written over here, this which we have written over here is nothing but the expression for the current element IDL, which means that this value over here, or this equation over here, is nothing but the magnetic field, okay, magnetic field at the center of the coil, the magnetic field at the center O of the coil due to that small element. But over here we have many elements. Okay, so in order to find the magnetic field due to all those elements, what do we have to do? We have to integrate over the equation. Okay, so from here, if we integrate over the equation, we get 1. Okay, so from here, let us mark that as equation number 2. Okay, let us put this as equation 2. So the total magnetic field due to the whole circular coil can be obtained by integrating the above equation 2. So from here, that means integration, okay, integration over dB, okay, integration over dB, okay, that will give us what? That will give us the total magnetic field B. that will give us a total magnetic field B. So integrating both left hand side and right hand side, that means integration over here, integration over here. So this will give us mu naught divided by 4 pi. Then over here you have what? I, okay, dl, okay, sine theta divided by 1, sine theta divided by r square. But when you look from that figure, it is obvious, okay, it is obvious, okay. But here, for the direction of that current element ideal bar and our radius vector r, r1, are perpendicular, okay, are perpendicular. So if they are perpendicular, which means that the angle between those two vectors, it is what? It is 90 degree. Let us recall, let us reiterate from the figure. From the figure, it is very evident, okay, it is very evident that this is the direction of our current element, thumb pointing in this direction, ideal. This is the direction of the current element. And from here, this is the direction of what? This is the direction of what? Radius vector. So ideal and r vector, r1, are 90 degree with respect to each other. Okay. Even for this case also, the thumb is pointing in this direction, since current is moving in this direction, current in this direction, so that will be ideal bar. And our radius vector in this direction, so radius vector in this direction, so this will be our r bar. So the angle between ideal bar and r bar is what? It is 90 degrees. So it is for every point, okay, for all the entire elements within this circular coil, the angle between ideal and r bar, the angle between ideal and r bar is always 90 degrees, which convinces us that theta, the value of theta should be what? The value of theta should be 90 degree. So when we substitute on this equation, okay, it implies that this B, okay, this B will be equal mu naught and 4 pi is constant. So you can take that outside of the integral sign, and then from here, that means we can simplify itself over here. Mu naught by 4 pi can be taken outside of the integral sign, and then we have this integration over ideal. Over here, this will give you 1. This will give us sine of 90 degree divided by 1, divided by r square. But sine of 90 degree is equal to 1. Okay. Over here, sine of 90 degree equal to 1. Since sine of 90 degree is equal to 1, therefore this expression, okay, this equation, I can write this as equation 3. This equation 3, okay, that equation 3 reduces to this form. Okay. I can simplify, reduce the steps as much as possible. So this equation 3 reduces to the following step. Okay. Therefore, 3 implies this equation. So from here, we have only a simple equation of I dl divided by 1 divided by r square. Even from here, the current which is passing through that coil is steady, so we can take that I term outside. Okay, we can take the current term outside, and r square also outside. So this current I also will be taken outside of the integral, and r square also outside of the integral. We are left only with integration over dl. Okay, this is our B. But what is dl? What is dl? So from here, but if we integrate over the entire coil, which if this is the circular coil, I have divided into many elements. Okay, dl. All these are what? dl, and r is the radius. If I sum over all these current elements, that means it will be equal to what? This will be equal to the circumference of what? This will be equal to the circumference of what? Of the coil. Okay, circumference of the coil. So this will be equal to the circumference of the coil. So which means that this expression, okay, this expression now reduces to, I can write over here, this expression reduces to B equals sine mu naught divided by 1, 4 pi, okay, I can write mu naught I divided by 1, 4 pi r square, and over here, integration over dl is twice pi r, so I can simply write twice pi r. Then from here, some of the terms will get cancelled, R, 1R and 1R will get cancelled, pi and pi will also get cancelled, 2 and 4 also will get cancelled. So it gives us the final expression, okay, the final expression for B, which is equal to what? Which is equal to mu naught I divided by twice R. This is that expression. This is that expression for the magnetic field due to that circular coil. Okay, due to that circular coil. But if you have a coil having n turns, for a coil having n turns, or for a coil having for n turns on a coil, that means you have, instead of only one turn, you have many turns on that coil. That means over here you just multiply that equation by n. You're multiplying that equation by n, then it will give you this expression, twice pi mu naught ni divided by twice pi r. So that is the expression. Okay, this is your expression for the magnetic field. Okay, magnetic field at the center O of the coil, or at the center O of the circular coil, which means that from here, this magnetic field is inversely proportional to R, under the condition that if I is current. That means if R is large, okay, if R is large, that means B will be what? B will be small, and if R is small, B will be large. So that is the main idea that we need to know. And this gives you only the idea about what? Only the idea about finding what? Finding the magnitude. Okay? Finding the magnitude of the magnetic field. Okay? Finding only the magnitude of the magnetic field due to that circular coil. But in order to find the direction, you have to use those right hand palm rule and right hand grip rule, which I have discussed previously. Okay, so the direction of this magnetic field at B, okay, can be obtained by using the right hand palm rule, number 1, okay, or by using the right hand grip rule, okay, number 2. So in that figure 1, the current is in the anti-clockwise direction. So if from here, the current, this is the coil, okay, this is the coil, the current is in the anti-clockwise direction. So if the current is in the anti-clockwise direction, okay, this is our one. This is our current element, and this is our R vector. So from here, the direction of our current element will be what? Will be indicated by, will be the dot which is pointing upwards. So from here, it is perpendicular, which means that the direction of B at the center O of the coil will be perpendicular. So the direction of the magnetic field, will be what? Will be perpendicular. Perpendicular to what? Perpendicular to I dl bar and R bar, and is directed out of the page, which means that if you are writing on your paper, that means it is out of the page. If you are looking at the screen, that means it is out of the screen, and it is represented by what? What is this? This is a dot mark. Okay, so you have to represent by the dot mark. Another important point to focus, okay, that is, recall a summary. We have this coil, and the currents from here, the current is moving in the clockwise direction. Next, the current will be moving in the anti-clockwise direction. Okay, the current will be moving in the clockwise direction. I mean, okay, this is anti-clockwise, and this will be the current moving in the clockwise direction. So from here, even consider this as the current element. And if I consider that as the current element, that means the direction of IDL will be on this direction. So this is the direction of IDL. This is the direction of R. So when you find the magnetic field at the center of the coil, so it will, your palm would be facing down. So we indicate by the cross mark. So the current so from here, even if the current is in the clockwise direction, keep in mind that the magnetic field is always what? Is always perpendicular. B should always be perpendicular. Magnetic field should always be perpendicular to IDL and R bar, because the B is our third vector. From here, that means it is always perpendicular to IDL and R bar. And if it is in your page or paper, it will be directed into the page. Okay, it will be directed into the page. And if you are looking on the screen, that means the direction of DB will be into the screen, and it is represented by what? And it is represented by the cross mark. In the former case, The direction of B is directed out of the page or out of the screen. So you just go through those important things that I have discussed with you, and keep in mind that this derivation is important from examination point of view. Preferably it will be a 3 marks derivation. Thank you.